Yes.
Okay, thank you. I am going to go to calendar and show you the next dates to complete the test 2. Okay, today is September 15th. So we're going to go through chapter 3 and chapter 4 material and going to have a test on October 6th, test 3 on chapter 3 and 4. The procedure for module 2 is just like for module 1. You have to take 2 quizzes, quiz 3 and quiz 4, and go through question and answers for chapter 3 and 4 and do the test 3. All right. So I'm going back to my slides on chapter 3 and start from there.
Yes.
Okay, thank you. I want to make sure they're there. Okay, we're going to have a test on October 5th. Now, chapter 3 is on chemical bonds. So far, we talked about the way we do science using scientific method and the composition of matter based on atoms, molecules, and ions. We've gone over that in chapter 1 and 2. Now we come to the point that we have to explain reactivity of elements. Elements make bonds. They don't exist as isolated atoms, except noble gases. So there are 2 types of bonding normally we see in atoms, normal atoms, not the noble gases. They are based on, bond formation is based on octet rule for atom. Each atom of an element, try to get an octet of electrons, is called octet rule. We're going to talk about that in more detail. One way to make octet of atoms, octet of electron in atom is to form anions and cations. Atoms lose electrons, form cations. An atom losing, gaining electrons, form anions. Anions are negatively charged, cations are positively charged. So that's one way to make bond. That bond is between ions are called ionic bond. Ionic bond is one of the 2 major types of chemical bonds. We're going to first look at it. Ionic bond in this chapter. And also we're going to look at how to name, given the formula of ionic compound, how to name the ionic compound. Then we're going to go to covalent bonds. Covalent bonds are based on achieving octet of electrons for atoms sharing electrons. So we're going to see covalent bonds. There are 2 second type of chemical bonds. First is ionic bond, second is covalent bond. We also have to deal with how to name covalent bonds, bonded compounds, which are normally molecules. So naming is different for ionic bonding and covalent bond. One of the aspects of covalent compounds is when we try to describe the structure of covalent compounds, we have to use more than one structure to describe the properties. I'm going to talk about that more detail as we go there. Now, in covalent bonds, there are bond angles between three different atoms. For example, water has about 104 degrees between the oxygen-hydrogen, two oxygen-hydrogen bonds. So we can predict bond angles based on the bonding theories we develop. We're going to look into this. Other important thing about covalent molecules is we need to be able to tell whether molecule itself has polarity, separation of charge. Okay, so we're going to look into that. Now, I have broken down objectives to several more items in this. I'm not going to go through this right now. Maybe after we complete the chapter, we come back and look at it. So octet rule is one. And we describe ionic and covalent bonds. And we talk about ionic bonds. We use periodic table to find whether compound is ionic or when a compound is formed between atoms, whether they are ionic or covalent compounds. Names of simple anion and cations. Give names of compounds from the formula. Recognize the bonding characteristics of covalent compounds. Naming covalent compounds. Now we draw Lewis structures for covalent compounds. Draw resonance structures. Resonance is several Lewis structures we use to describe an atom or molecule or ion. Lastly, we're going to predict one more item here. Predict the bond angles and shapes around an atom in a molecule. And lastly, we will know how to predict polarities of a molecule, whether they are polar or non-polar, based on our models. Now, the whole idea about octet rule. Octet rule is the main idea why atoms, non-noble gas atoms, are reactive. This idea was proposed by G.N. Lewis. Lack of chemical reactivity of noble gases is due to their stable electronic configurations. That's the idea. Therefore, other atoms which don't have octet of electron tend to gain electrons, lose electrons, share electrons in gaining an octet of valence electron. This is explained in here briefly. If you look at helium here, electronic configuration, we go through the periodic table. We talked about it, 1s2. Lewis also wrote a Lewis dot symbol. Lewis didn't know about electronic configuration when he finished his work, octet rule. But you can see it's following the basic structure of electronic configuration of elements. So Lewis dot symbol shows 2 electrons, 2 valence electron on helium, like this. 8 electrons in all others. If you look at all other noble gases, there are 8 electrons. 8 electrons are counted based on last shell. 3 here, 3 here, 2 here on the previous one. 3D is not counted for this, not the valence shell. Valence is the highest numbered shell number orbital. So valence shell is for xenon is 5s and 5p. So whole idea is, except helium, all other noble gas has octet. Helium cannot have more than 2 because it is limited by atomic orbitals. Only 1 atomic orbital, 1s is there. Therefore, helium has duet of electron rather than octet. Now, octet rule is the basis we use for main group elements. Main group elements are, if you look at the periodic table, this is in the middle is the D block. That's the S block. There are 1A, 2A, 3A, 4A. I'm going to show it in the periodic table in a minute. These main groups are excluding noble gases. These tall columns are called main groups. So we are mainly concerned about main groups, this group and that group. They belong to 1A through 7A labeling of the groups. So they achieve octet of electron, except helium. Helium is a noble gas. Anyway, all others are octet of electron. An atom that loses 1 or more electrons to become a positively charged ion called cation. An atom can lose 1 electron. I'm going to explain it in the next slide, how the sodium does it. Atom that gains 1 more electrons become a negatively charged ion. It's called anion. There are 2 ways described here. Either you can lose 1 electron and go back to preceding noble gas octet. Anion gain electron, go forward to the next noble gas configuration. An atom can share more than 1 electron to form molecule. Sharing creates covalent bonds. Gaining and losing electrons, cations and anion form, lead to ionic bond. So these 2 bond types are both explained by octet rule. Now I'm going to go to more into ionic bonding. In forming ionic bond, cations are formed. In losing 1 electron, sodium atoms form a sodium ion, described below here. Sodium has 11 electrons. Valence shell is 3rd shell, has 1 electron. Lewis showed the Lewis dot symbol based on that. We are mainly using the Lewis dot symbol right here. So therefore, we need to know how to write the Lewis dot symbol for any main group element. Then when sodium loses 1 electron, it becomes 10 electrons. Now you have an octet of electron. This whole thing is a core of neon. So now sodium plus ion has become neon-like octet. So they achieve the octet. That's how we'll explain. When a cation is formed from an element, atom of an element, it forms octet by going backwards to the next noble gas element. Anions also follow the same thing. Chlorine forms chloride ion, which has the argon structure. So this is the Lewis dot symbol for chlorine. It has one single electron. When it gains one more, this electron gains one electron, 5 becomes 6. Therefore, another dots go in here. It becomes argon now, going to the next noble gas octet. So therefore, it is clear that octet rule is followed when atoms lose and gain electrons. Now let's see. We only talk about one positive charge and one negative in the previous slide. The valence shell could have more than one electron, 2, 3, 4, 5, 6, 7. Now there are several ways to get to the octet. Normally, we talked about one alkali metal, which is sodium. Calcium is an alkaline earth metal. It makes 2 plus. 2 plus, I cannot write. That's perfectly okay. But when you make highly charged cations greater than 2 plus, they become unstable. Because to maintain highly charged ions, electrons are being repelled. Therefore, they are unstable. We never get boron 3 plus or carbon, which is in the group 4A. So highly charged ions are impossible. So in ions of group, these are the labels for the non-metals here mainly. This is halogens here, oxygen group here, nitrogen, not oxygen. Yes, oxygen is here, nitrogen is here, carbon is here. Now they never form anions greater than +2, -2. For example, carbon cannot make carbon -4. The idea is main group elements don't form large, highly charged cations or anions. They are like +1 to +3, -1 to -2, like that. Octet rule also don't apply to transition metals or inner transition metals. Transition metals are in the middle of the periodic table, in the deep square dip in the middle of the periodic table. Their transition metals bonding cannot be explained by octet rule. There's a limitation of octet rule. Now, we talked about ions. Making ions, you can achieve octet. We can also share electrons between two atoms, make molecules with covalent bonds. In sharing electrons between non-metals, notice this, these are all non-metals. Hydrogen also non-metal. They form molecule which has duet for hydrogen, octet for all other elements. Duet is hydrogen is in the group 1, can have only 2 electrons maximum. Therefore, hydrogen never get octet. So, for example, we explain how a water molecule is formed, starting with Lewis dot symbol for oxygen and 2 hydrogen. These single electron on oxygen and hydrogen, they become a bond. So they become a shared electron pair, which is called bonding electron pair, bonding electron. It's hard to write here. Bonding electron pair. This is a bonding electron pair. I write it bonding electron pair. Non-bonding electron pairs, lone pairs, they are not found between 2 atoms. Still, it's a pair. So in molecules, we normally have bonding electron pairs and non-bonding electron pairs when they form the structure molecule. We can also explain bonding between hydrogen, 3 hydrogen, and nitrogen here, similar to that. 3 bonding electron pairs are formed, 1 here, 1 here, 1 here, 1 lone pair. So bonding pairs are sometimes you replace 2 dots with a line here, line like that. So it's shown. Water has 2 bonds, 2 OH bonds. Ammonia has 2 NH bonds. Now, important thing is nitrogen has octet, oxygen has octet, hydrogen is a duet here. Around hydrogen, there are 2 electrons. So therefore, they follow octet rule for all elements except hydrogen. Hydrogen follows duet rule. Now, methane is a natural gas. Methane is natural gas. It has 4 hydrogen atoms bonded to carbon. Carbon make 4 bonds. Carbon don't have lone pairs. This is 4 bonds here. Carbon has octet. Hydrogen has a duet, like that. So that's how we explain octet rule for covalent molecules, covalent compounds. Molecules are covalent compounds without charges. Now, forming chemical bonds, we describe there are 2 ways: ionic bond, gaining and losing electrons, covalent bond. According to Lewis model, an atom may lose or gain enough electrons to acquire a filled valence shell and become an ion. So they don't just lose electrons randomly. Their purpose is to lose them or gain them and get to the octet of electron. An ionic bond is a result of force of attraction between cation and an ion. Now, ionic bond is a byproduct of losing, gaining electron, producing ions. Ion has electrostatic attraction. That's a very strong force. Therefore, ionic compounds are solid. Atoms may share. This is the covalent. This is the ionic bonding. This is ionic bonding, covalent bonding, CBIC. They share electrons like water, hydrogen and oxygen in water, ammonia, C and hydrogen share 1 or more pairs that can accomplish octet for all atoms in the molecule, duet for the hydrogen. Now, periodic table, I'm trying to explain. These are the 2 A's. These are the 3 A's and 7 A's here. These are the main group elements. Okay. They are the ones we apply octet rule. We cannot apply octet rule to this or lanthanide, actinide, or inner transition metal. So to get the valence electrons, lithium has only one, because only one place from the left. 2 place, beryllium has 2, boron has 3. So it's easy to get the Lewis dot symbol from the periodic table. We're going to talk about electronegativity in a minute, another criteria to predict ionic and covalent bond formation. So I just shown the labeling on the periodic table here. Now, one of the criteria we use to predict whether bond between 2 elements, oxygen, hydrogen, sodium and chloride, those 2 pairs, whether it's ionic, covalent bonds. We use the scale developed by Pauling. I probably have missed a scale developed by Linus Pauling. He put certain numbers in the periodic table. Now periodic table do not have elements, do not have atomic number here. The number here is called electronegativity. Pauling came up with the idea. Some atoms have strong tendency to pull electrons from atoms, other atoms in a bond. For example, if you have a bond of oxygen and hydrogen, fluorine and hydrogen, the fluorine pulls more electrons in the bond towards it because it has a higher electronegativity number. So electronegativity is used to predict the attraction of each atom, main group atoms, including all transition elements, how strongly they are attracting electrons in bonds. So electronegativity values increase this way, going from the bottom, and increase this way, going across the period. So lowest electronegative, which have lowest attraction to electrons in a bond, in a molecule, is found here. Highest is found in fluorine. So this scale developed by Linus Pauling is used to predict whether 2 atoms make ionic bonds or covalent bonds. It's a measure of atoms' attraction to the electrons it shares in a chemical bond with another atom. This is not an atomic property. It's electronegativity. We are talking about in a molecule, particular atom attracts more electrons in a bonding electrons towards it. Fluorine is the highest. Lowest is rubidium, or left bottom. On the Pauling scale, fluorine is the most electronegative element, and it has assigned a value of 4. And all other atoms are lower than that value. Electronegativity is a periodic property. We describe this. Going up a group, it increases. Going across the period is increases. So you can compare two elements and say which one has more electronegativity. Now we're going to use the idea how we predict ionic or covalent bond formation. Now we have to know ionic bonds once formed is just the attraction between ions. There's no electrons are completely lost or gained by anions. Covalent bond is a tricky situation. If you have higher electronegative elements, they pull the bonds in the electrons in the bond towards it and create a polarity. So covalent compounds are either non-polar covalent bonds or polar covalent bonds. There are two types of covalent bonds: polar covalent bond, non-polar covalent bonds, no polarity, polar covalent bond, polarity is there. How you predict that from electronegativity is the next idea. Normally, metals have small electronegativity values because they are found in the left side of the periodic table. Non-metals are found on the right side of the periodic table. Therefore, when you calculate the electronegativity difference, right here, En difference, we call it delta En. Delta is a difference. Electronegativity difference. You can calculate for two atoms of two elements. A covalent bond is, they have larger electronegative differences, ionic compound, large. Other way around, it's lower. I think difference is larger here. Lower delta En. So we're going to look into this. You can predict from the electronegativity difference whether it's an ionic compound or a covalent compound, covalent bond, ionic bond or covalent bond is formed from bonding between two metals or two atoms. If the electronegativity difference is 1.9, I'm going to show you in a minute, it is greater than, difference has found to be greater than 1.9, it's ionic bond. It's less than this range, less than 0.5, it is non-polar covalent. It's greater than 0.5 and this range is polar covalent bond. We take an example in a minute. Ionic compound. Let's go back and do this. Okay, I'm going to do sodium chloride. The electronegativity difference is sodium is 0.9, chloride is 3.0, 1.9 differences. 2.9, right? 2.1. Three minus 0.1 is 2.1. Now 2.1 is greater than 1.9, therefore it is ionic bond. For example, oil and hydrogen. Hydrogen is 2.1. How do I get? here. Oxygen is 3.5. The larger value subtracted smaller value, 4, 1.4. Now 1.4 is between 0.5 and 1.9. Therefore, this is ionic, this is covalent. So this is the idea. You can get the values for anything. A bond is sodium chloride has a greater than value 1.9, 2.1 or something I calculated. 1.4 for OH bond. OH bond is polar covalent. All right. So you can tell whether bond is ionic, polar covalent, non-polar covalent, or polar covalent. All right. So that's very useful when you're trying to describe bonding. Now we're going to ionic compounds. We have to know how to name ions before we describe them. Ions are cations and anions. We are going to start with cations first. Now, one rule is 1A, alkali metal like sodium, alkaline earth metal like calcium, aluminum, air, have only one type of cation. That means sodium always make positive 1. Calcium make only positive. Aluminum always make 3+. The group number gives the number of charge on the cation. So this is, as a rule, you can take that. The name of the cation is the name of the metal followed by the word ion. If you look at this, hydrogen is the name of the element. Hydrogen makes only 1. The group 1A always make positive 1. Ion is H plus ion is called hydrogen ion. Magnesium ion is Mg2+ because magnesium always only form 2+. Calcium, alkali metal group 2A, only form 2+ ions. Aluminum group here, aluminum always make 3+ for sure. Magnesium group followed by calcium, strontium, barium forms 2+ ions. The name of the metal element followed by ion is the magnesium ion. So if someone asks you magnesium ion, what is the symbol? Symbol is Mg2+. Calcium ion, what is the symbol? Calcium 2+, like that. Do you guys following this? Are you there?
Yes.
All right. So now naming cations with variable charge, that's mainly transition elements and actinide and lanthanide. Unlike group 1A, 2A, 3A, they have fixed charges. Transition metal have variable charges. That means more than one cation with different charges. To name them, we use 2 systems, a new system and an old system. I'm going to explain how you name cations with variable charges. For naming cations derived from transition metal and inner transition metal, which has more than one type of cation, there are 2 options. Systematic is the new one. You use Roman numerals. Roman numeral is parentheses. Do you know what Roman numerals are? 1, 2, 3, 4, 5 in parentheses after the name. You have to tell like iron is exists in 2 plus or 3 plus. So you have to, what is the iron 2 plus name? Fe2 plus name. Iron parenthesis 2 plus. Iron 3 plus is, Fe3 plus is iron. We're going to look at the details here. Older system is, the lower charge is called ferric and higher charge is called, lower charge is called ferrous, higher charge is called ferric, 3 plus. If you have 2 charges, the name is changed to ask for the lower charge ion, equal to the higher charge ion. That's the older system. Let's look at the table in here. So these are transition metals and mostly metal atoms that make more than one cation, variable charge. Copper ion, copper 1 plus. That's the parentheses. You put the parentheses 1, which is the 1 charge, and you add the ion to all the cations. Name with the parentheses ion. This is the older system. This is, copper has 2 charges, copper 1 and copper 2. Highly charged ion in the older system is called Ec, high charge. Lower charge one is called Cupri. This system is much easier, but sometimes we, in the bottle label in the lab, follow the older system. So you need to kind of to find out what charge is on the metal variable charges, metals variable charges. Copper comes from name cuprum. Cuprous, cupri. Ferrum comes from the Latin name iron. Hydrogyrium is the mercury. Stannum is a Sn. So do you understand, to name a variable charge cation, you have to use a parenthesis to indicate what charge is on the ion, right? Because there are 2 possibilities. We're going to do more problems. It might be clear. So we are going to anions now. We talked about cations, how to name fixed charges and variable charges. Variable charges with cations with parentheses number. So for anions, there are monoatomic ions, anions. They gain 1 electron. Examples of monoatomic ions: hydride, hydrogen, fluoride, chloride, bromide, iodide, oxide, sulfide. So you don't keep the element name. You abbreviate element name to a stem: hydra, flora, fluor, pro, and add the I. INE, chlorine, is dropped, and ride is added. See, that's ride. Ride means anions, iodide. You don't call chlorine chloride. This is the chloride. You understand that? This is hydrogen. This is hydride. This is bromide. Bromide is here. Bromine become bromide. So depending on the non-metal, you add a I to the end. All right? Oxide has 2 negative charge. Sulfide is also having 2 negative charge. Now, this story is a little more complicated. Ionic compounds have polyatomic ions. Life would have easy if you have just metals and monoatomic anions like chloride, bromide, iodide. But there are complicated molecules with charges. These are group of atoms. This has to be, that ammonium is kind of wrong here. Ammonium ion is 4+. All right. Ammonium ion is the only polyatomic ion with the cation. It's a cation. All the metals are mainly monoatomic. Hydroxide is this. It's an anion. This is a cation. Nitrite, nitrate. Nitrate is NO2 minus. Nitrite is NO2 minus. Nitrate is NO3 minus. What is the difference between nitrate and nitrite? 1 oxygen less. It's called ite. Ite means have less oxygen. Acetate ion is also common polyatomic ion. Perchlorate, ClO4, cyanide, permanganate, CrO4 2 minus, chromate, dichromate, CrO2 2 minus, dichromate. Hydrogen carbonate. What is carbonate? Carbonate is not here. Carbonate is an important one. Carbonate is CO3 2 minus. Hydrogen carbonate is when you add a hydrogen ion, charge reduce HCO3 minus, hydrogen carbonate. Sulfide and sulfate are like nitrite, nitrate. One less oxygen. So is this, right? Less oxygen. Hydrogen sulfate, also called bisulfate, bicarbonate, bisulfate. Bi means hydrogen. Phosphate, 3+, 3 negative. PO4, 3 negative. Hydrogen phosphate is like biphosphate. Hydrogen is added to phosphate. It becomes 2 negative now. Hydrogen phosphate. Dihydrogen phosphate, 2 hydrogens added, 1 negative charge. So charges on the polyatomic ions should be remembered, or most difficult one I will give a list of in the test, okay, to name the polyatomic ions and use them in naming ionic compounds. Ionic compound is formed between attraction of cations and anions. In forming sodium chloride, 1 electron is transferred from the sodium to the chlorine atom. Just this is electron configuration description. This is not necessary. Use a single-headed curved arrow to show the transfer of electron. 1 electron is from the sodium is transferred to the chloride here. Chloride has extra electron. They both are octet transfer. The charge attraction is an ionic bond. Now we are at the point we need to get the formula of ionic compounds. Okay. Total number of positive charges might be equal to the total number of negative charges. If you knew two ions that combine, like sodium chloride, for example, what is the formula of an ion found from sodium and chloride? They are balanced now. Therefore, you drop the ion charge, you write down sodium chloride. Lithium bromide, just like sodium chloride, formula is this. The charge is balanced, one here, one here. Now is the problem, two here, one here. Therefore, to balance the charge, you cross multiply. The charge on barium is the 2. Charge on iodine is the on the barium. Charge is -1. This 1. You drop the charge. You need 2 iodine to balance the, must be equal to the total number of negative charge. Charges must be equal. So barium is, an iodine is barium, Ba(I2). Aluminum has 3, sulfur has, charges are not balanced. When you have something like this, that's the best way to look at it. Aluminum, the charge is 2 minus, 3 plus. You cross this, you get that one. When you cross the 2 here without the charges, Al2SO3, aluminum sulfide. We call it aluminum sulfide. Sodium bicarbonate, their charge is balanced. You drop the charges, you get the sodium bicarbonate. Potassium 1, 3. Now in this case, 3 has to go in here. Like this one is 1, we don't write parentheses for 1. So that's K3PO4. So it's really easy when you know the ion names and how to get the name of the formula of the compound. Okay. Binary covalent compound. Binary means 2 elements. The name of the metal is written first from the formula. How do you get the name? Followed by the name of the negative ion. Subscripts are not directly specified in the name. You don't say Al aluminum trichloride. You don't call it. Why? Aluminum, we know, always have 3 plus. Chloride has 3 negative. We don't have to charge balance. We can find out in the formula it's charge balance. You don't write the subscript, you just say aluminum chloride. Lithium bromide is lithium bromide. There's no problem with subscript here. Magnesium oxide is also written as it. Do you know charge on the magnesium? What? 2 plus. Oxide is 2 minus, is charge balance. Silver sulfide. Silver is +1. Sulfur is -2. Therefore, we don't call disilver sulfide. We don't use prefixes to show the name of ionic compound, ions, type, number of ions. Potassium chloride is just plain potassium chloride. Lithium hydride. Hydride is -H. Lithium is +H. They are charge balanced, lithium hydride. So it's pretty easy to get the charge of the cations and anions. From there, you get the name, formula, etc. All right? Now, let's do this one, cation with variable charges. Variable charges is, with the parentheses, we write down the charge number or use the old system, S and E. Remember, highly charged is cation name and with the E, low charge name with the S ending. So copper oxide, how do we know copper oxide is 2? Given the copper oxide formula, this should be charge balance. So therefore, copper need to have 2 plus. So 2 plus is shown here. That's the name of copper oxide, copper 2 oxide. This is the older system, RC. Cupric is the highest. Copper has Cu plus, Cu 2 plus, 1 plus, 2 plus. 1 plus is cuprous. That's shown here. How do I know it's 1 here? If you have oxygen always have 2 minus. So therefore this group should be 1 each. So therefore 2 coppers with charge 1. So that's the charge 1. Cuprous oxide, lower charge. Iron oxide. How do I know iron is 2? Oxygen is always 2 minus. Therefore, iron should be 2 plus. Charge balance. Formula has to be charge balance. Therefore, this 2 comes from charge of the metal. Older system is called ferrous. Lower charge is Fe2. Fe3 plus is the next one. So to figure this out, you have to have 2 minus. That's 6 negatives. This total charge is 6 negative. So there are 2 of them. Therefore, each one should be 3 plus. So that's how you get the plus charge in the parentheses, 3. Highly charged ion is ferric, so older system. Now, how many of you understood that? So this is going to be more practice. The name of ionic compound that contain polyatomic ions. Now we are naming compounds with polyatomic ion. Name the positive ion first, just like in other cases, followed by the name of the negative ion. If you look at the formula, sodium, this is the sodium. This is the nitrate. Nitrate is 1 minus. Sodium is plus 1. They are charge balance, sodium nitrate. You don't write prefixes. You don't call it monosodium nitrate, mononitrate or anything. Calcium also, you can check charge balance. Calcium has 2 plus. Carbonate ion I wrote down in the previous slide. Carbonate ion has 2 minus. The charge balance. That you need to know this is carbonate ion, polyatomic ion, calcium carbonate. Now you know sodium is this one. Now what is the name of this? Dihydrogen phosphate. So it was in the list. Ammonium ion here, positive one, hydride ion. We call ammonium hydroxide. OH is hydroxide. Iron 2 carbonate. Iron is 2 plus here, carbonate, or ferrous. Iron 2 plus is ferrous carbonate. Variable charges in transition metals. This is iron 3 plus. So iron 3 plus carbonate. Highly charged ion is called ferric carbonate. Copper sulfate. Copper is 2. This is negative, always -1, -2, I'm sorry, -2. Sulfate is -2. If you look at the table, therefore this should be positive to charge balance. Therefore 2 here. It also called copper 2 sulfate or cupric sulfate, highly charged copper ion. This is called barium hydride. Hydride is the H minus, right? Now, to summarize all these, let's start with this. If you have formulas given like this, what are the ions and charges? You can break down sodium into sodium ion and nitrate ion. So this is sodium, calcium, sodium, ammonium, iron. This is 2 plus, 3 plus, copper, 2 plus. Charge balance will tell you what are the charges on the cation. Then you go to the anion name. Cation name is sodium ion, calcium ion, sodium ion, ammonium ion, iron 2 plus, 3 plus, copper 2 plus, variant. So now this is the cation name. That's the anion name. Nitrate, carbonate, okay, dihydrogen phosphate here. You just separate them out. So you get the sulfate here, hydride here, barium hydride. So name of the hydride, anion, nitrate, carbonate, dihydrogen phosphate, hydroxide. So you cannot translate them to names, formula. So formula to ions here. And then you got the names of cations and names of anions. So then finally you put these two columns together into the final name. Sodium nitrate, calcium carbonate. So this is the complete list of ferrous or ferric, cupric, etc. All right. Now I am going to stop at this point because we are done with ionic bond. We described the cation names, variable charge with names for cations with variable charges, anion names, polyatomic anion names, and we put together how to get the formula and a compound name for ionic compound. So we're going to start with covalent bond in the next class period. All right. You guys have any questions?
No, sir.
All right. I'm glad you guys still hanging around. I was keep talking and didn't notice you guys are there or not. Okay. See you on Tuesday, next Tuesday, same time. All right.
Okay.
Okay. Sign the class roll. I mean, chat box. Okay. All right. I'm going to stop this share and stop the meeting.